So, Bismillahirrahmanirrahim. Are you able to see the screen now? So, yes. So, hopefully you are able to see the screen, right? So what I was
Yes, sir.
what I was describing was that we we have phase voltages and line voltages. Likewise, we have phase currents and line currents, right? So, for example, this is this phase current here. Phase current IAB is the phase current for this phase. Current IBC is the phase current for this phase, and current ICA is the phase current for this phase. And this is the line current here, IA, IB, and IC. So, in this case, the phase currents are not equal to the line current. These are the different, right? But in this case, if you see, this is the phase current here, and this is the line current here, and topologically, this is basically the same current. So, for a Y-connected load, the line current is the same as the phase current. But for the delta-connected load, the line current is not the same as the phase current. So, we need to find out the relationship between the phase current and the line current for this delta-connected delta configuration, right? So, one more point, when we talk of voltages, phase voltages and line voltages, we mean and we imply the phase voltages and line voltages of the source, right? And as you have seen, when we talk of the line current and the phase current, we mean and we imply the line current and the phase currents flowing through the load, right? So, and as we have seen also, for Y-connected source, the line voltage is not the same as the phase voltage. These are different. But for delta-connected load, the line voltage is the same as the phase voltage. Similarly, for the load, if the load is Y-connected, then the line current is the same as the phase current. But if the load is delta connected, then the line current is not the same as the phase current. Topologically, this is not possible. Okay? And as I have described, the source describes the configuration of the voltage sources, whether it is Y or whether it is delta. It describes the relationship between the phase voltage and the line voltage. And the configuration of the load, whether it is Y connected or delta connected, it describes the relationship between the line current and the phase current. So let's find out the relationship between the phase voltage and the line voltage for a Y-connected source. For Y-connected source. So as you see, VAB, for example, this is the line-to-line voltage VAB. We are interested to find the line-to-line voltage VAB, right? So if you see here, so VAB is equal to VAN and then minus VBN or plus VNB. VNB is in this direction, right? And VBN is in negative direction. VBN is in this direction, right? The polarity is opposite. So this is VAN minus VBN. So VAB is equal to VAN minus VBN. And if we assume the positive phase sequence, then we know that VAN is equal to VP angle 0 degrees, VBN is equal to VP angle minus 120 degrees, and VCN is equal to VP angle plus 120 degrees. So in this case, then VAB is equal to VAN is equal to VP angle 0 degrees and minus VP angle, put the value of the VBN, this is VP angle minus 120 degrees, right? So we take VP common, so VP, so this is 1 angle 0 degrees minus 1 angle minus 120 degrees. So if we transform this to rectangular form, so 1 angle 0 degrees is 1 plus j0, so this is 1, and this will be cos minus 120 and plus j sine minus 120 degrees. And if we find out the values, this will be cos 120 is cos minus 120 is minus 1 over 2, so minus 1 over 2 will be plus 1 over 2, right? And minus sine 120 degrees will be j under root 3, j is for the imaginary part, right? Under root 3 over 2. So this is in effect equal to VP, this is 3 over 2 plus j under root 3 over 2, right? And if we now transform this back to the polar form, so this will be 9 over 4 VP multiplied by 9 over 4 plus 3 over 4 square root multiplied by VP, and the angle will be tan inverse under root 3 over 2 divided by 3 over 2, right? So VAB is equal to 9 over 4 plus 3 over 4, that is 12 over 4. So the 12 over 4 is 3. So square root 3 VP, and tan inverse under root 3 over 2 is over 3 over 2, 2 cancels out, and we are left with tan inverse 1 over under root 3, that is 30 degrees. So this is basically the value of VAB, the line voltage in terms of the phase voltage, right? So we see that the phase voltage, the line voltage leads the corresponding phase voltage by 30 degree. So in a similar manner, we can see that this was VAB, right? We calculated VAB here, VAN minus VBN. So likewise, we can calculate the value for VBC also. So VBC is equal to VBC equal to VBN minus VCN, right? VBC is equal to yes, VBN B2N and then minus VCN. VBN minus VCN. And if we perform a similar procedure like this one here, and then we can find that the value of VBC comes out to be something under root 3, the magnitude remains the same, under root 3 VP, and this will lag this by 120 degree, right? So if this is 30, so 30 minus 120, so that will be minus 90 degree. Minus 90 degree. So similarly, VCA will be given by VCN minus VAN. VCN is given by VCN is given by VCA is given by VCN minus VAN, which is in the opposite direction. So for the opposite direction we take the negative sign, and this again lags this by 120 degrees, so the magnitude remains the same. If we perform a similar calculation as we did for VAB, we will find that this is under root 3 VP, and this is minus 90 minus 120, that will be minus 210 degrees, or minus 210 degrees is also represented as 150 degrees, right? So these are the